Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is Digital 1. Today we're going to discuss codes using binary numbers. As we last saw in our lecture, I introduced something called the 2's complement representation of numbers. It is different from traditional straight binary representation numbers, but it's still using binary numbers 0 and 1 in a positional relationship. Okay, so we have our straight binary representation of a number, our 2's complement representation of a number, and again, let's do, here I'm going to go ahead and just do a table. And there is our table representing all possible combinations of zeros and ones. And again, if you're a drummer, you've probably seen this like in high school when you're doing all the possible rhythm combinations of 16th notes. Just used to that. Get used to this. 0 1 0 1 0 1 0 0 1 1. 4 zeros followed by 4 ones. 8 zeros followed by 8 ones. And I just wish I had a stamp on this. Just stamp it out. You're gonna get used to that one. Okay, so binary, if we're using straight binary, 0, 1, 2, 3, 4, all the way to 15. Two's complement, remember, the leftmost bit is going to be a negative number, so that's going to be our -1. And the first 8, one moment, it's a 1 and a 0. Okay, so we're again using the same 4-bit positions, but they mean two different things. It's two different languages. So these are not the only two languages that you should probably be familiar with. Okay, so there's something called BCD, and that stands for binary coded decimal. So binary coded decimal, that's the key point. We're trying to code decimal numbers. What are our decimal numbers? 0 to 9. There's nothing else beyond that, because if you go to 10, you're still using two decimal numbers, 1 and a 0, namely. So binary coded decimal uses 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, and that's it. This is invalid. Okay? So who uses BCD? Well, think about a display, a clock display, a 7-segment display. It displays one decimal number. It can't display a 10 in one 7-segment display, because to display a 10, you would need two, namely a 1 and a 0. Okay, so each display is displaying one decimal digit. And that is key because the only numbers it's going to recognize is 0 through 9. So you send it a 3, send this guy a 3, it's going to show a 3. If you try to send something that's expecting BCD, any of these numbers, what does it do? Well, it wigs out because it's invalid. Okay, so just here's the rule. Don't send, and you're going to do it in one of the labs. You're going to do it, see how the 7-segment display behaves when you send it an invalid number. There's some funky things that happen to a 7-segment display when you send it an invalid number. Okay, the other key thing is to remember is if you get a display that's wigging out, that's displaying some weird things, and you think you're sending a correct BCD number, make sure your numbers are routed to an appropriate place. For example, the number 6, 0, 1, 1, 0, if sent to a 7-segment display correctly, should display a 6. But what happens if you mistakenly transpose these numbers? You're sending 1, 0, 1, 0, which, as we know, is an invalid representation of binary coded decimal. And you send it to the display, and it starts on fire. It doesn't start on fire, by the way. You're sending a correct number, but you've mistakenly swapped these bits right there. So your display is displaying something weird. Check your work. It may not be the display. Check your routing of the data. And that's the key thing, too, to remember in some of these labs. Stay organized. That's the first principle. First principle, stay organized. Second principle, stay organized. Third principle, stay organized. And the fourth and final principle is, if you don't stay organized, start predicting some of the errors. So that is an error that you're going to start predicting. Okay, maybe I do have something disorganized and I'm seeing an error, and what is causing that error? Okay, so BCD is a truncated version of traditional binary. Now, if I was to represent a number like, let's say 42, I want to represent that in BCD. 4-bit representation of 2, 0, 0, 1, 0, and the 4-bit representation of 4, 0, 1, 0, 0. Okay? So, whereas the traditional binary representation of 42, well, we couldn't do it in 4 bits to begin with. Okay, because we'd need a little bit more than that. So the traditional binary representation of 42, let's just do it in 8 bits. That's a 128, 64, 32, 16, 8, 4, 2, 1. No 128s, no 64s, 132, no 16s. There is an 8, no 4s, there is a 2, no 1s. So the 8-bit representation of 42 in traditional binary is 0010, 1010, whereas the representation of 42 in BCD is quite literally 42. Just a simplified version of traditional binary for devices that use and display only only decimal numbers. Okay? Okay, let's move on to our next discussion of codes. One of the more common, here's a code called octal, and here's my lecture on octal. No one uses octal, so forget octal. But people do use something called hex. Okay, all hex is, it's binary shorthand. Because look at this, your eyes are probably already glazing over with all those zeros and ones in there. And it's hard to remember if it's a 1010 or if it's a 1001. You know, it's easy to transpose bits sometimes. So what hex is, it's a binary shorthand. It's a shorthand of groups of 4 binary numbers. So I'm going to erase this and show you how you do that. So hex, it's binary shorthand. And look at this, you got 16 possible combos. And again, we could use the numbers, the decimal numbers, 0 to 15 to represent these guys. But look at these guys right here. 10 through 15 use 2 digits. So it's not exactly the most convenient. I want to have a single digit to represent 10, 11, 12, 13, 14, and 15. So how you do that is you use the traditional numbers 1, 2, 3, 4, 5, 6, 7, 8, and 9. But rather than going to 10, call that one A. You guessed it, B, C, D, E, F. Okay? It's shorthand. Rather than saying quadruple 0, I can just say, if I'm speaking in hex, I could just say 0. Rather than saying 0101, I could just say, if I'm speaking in hex, 5. rather than saying 1110, I could say D. Okay, so it's a shorthand way of representing extremely large strings of bits. If I say to use 05D and I'm speaking in hex, that means I'm talking about 1, 2, 3, 4 zeros, 0, 1, 0, 1. I'm also speaking of, where is D? Is 1, 1, 0, 1. Let me make sure that's correct. There you go. So if I say 05D hex or base 16, it's a lot more convenient than saying 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 0, 1. Did you get that? It's a lot easier saying 05D, base 16. Okay? So if I gave you a string of numbers, say 1 triple 0, 1 triple 0, 1 1 0 0, how would I represent that in hex? Well, break it up into 4 groups of 4, which I kind of did. Here's 4, there's 4, there's 4. So 1 1 0 1, that is C. 1 triple 0, 8. 1 triple 0, 8. 8 8 C, base 16. Okay? So now if I gave you the number 1 2, base 16, what is it? And your first answer, first wrong answer, oh, that's 1 1 0 0. That is incorrect, because that is 1 2 base 10 in binary. I'm looking for 1 2. 1 is, 2 is, okay? That is very similar to binary coded decimal, but what if I gave you 1A, base 16? 0 0 0 1, what is A? 1 0 1 0. Where that's A, that's 1. Again, hex, binary shorthand. Should be pretty easy. Okay, the next code I want to talk about is gray code. And gray code, I'm actually going to write over here. If I was to count in binary, 0 0, it's just straight regular binary, 0 1, 1 0, 1 1. Notice what happens in this transition from 0 1 to 1 0. The state of both my LSB and MSB must simultaneously change. Okay? Now this lends ourselves to a problem. What if our LSB changed before our MSB? 0 0, 0 1, and let's say our LSB changes before our MSB. 0 0, and then our MSB changes 1 0 1 1. So rather than this orderly straight counting from 0 2 3, we get 0 1 0 2 3. This is a brief error state, and it happens in binary systems using binary, regular straight binary numbering when things change out of sequence. So that's why the gray code was invented. The gray code is binary counting where one bit position changes and only one bit position changes at a time. So if I was to count in gray code 0 0 0 1, I couldn't go to 1 0 because both my MSB and LSB would change simultaneously. So I would have to change, in this case, keep the LSB as is, then change the MSB, then change the LSB. Okay? So this is gray code. And if you think it's easy with 2 bits, try 3 bits and 4 bits. Don't worry so much about counting in gray code just now. again, just be aware of what gray code's use is. It's trying to make sure that there's no error states in there. Look at this. This is an orderly transition. There is no brief error state because there's no brief error state in between here because only one of these guys is changing at a time. Whereas if you're simultaneously trying to change them and one bit position changes before the other, if you're trying to change a number of positions at the same time, things can happen out of sequence and you get these erroneous glitch states, which is basically a brief error position. Okay, gray code tries to prevent that. Okay, so that's one of the last codes I want to talk about. But the last topic for the codes is something called parity. Okay, parity, all it is, it's a simplified means of error checking. Like I showed earlier, it is so easy to transpose bits. Put a 1 where a 0 was, where a 0 where a 1 was, or swap positions. It's super easy to do that. Or to add a 1 where you shouldn't have a 1, or add a 0 where you shouldn't have a 0. So how you do that is use of parity. For our level of discussion, parity, all it is just a simple means of adding a 1 or 0 to a string of bits to make sure that what you send and what you receive are the same thing. And this is how you do it. Let's say we're trying to send the number, let's say 4. And I want to send it to my friend, and I want to make sure he's getting the number 4. How I do it is I add a parity bit to it. So in this particular case, let's use even parity. So even parity adds a 1 to an odd number of bits, okay, to make the whole string of bits even, okay? So how many bits do I have? How many ones do I have? There's none. Here's 1, none, none. So it looks like I have 1 in there. So to make 1 even, the next one up is 2, so I would have to add a 1 to this. So when I add up all the number of 1s in this particular string, 1 and a 1, that means 2, it's even. Okay? So that way when I send the number 0, 1, 0, 0 with a parity bit of 1, if I'm using even parity, my friend can verify, okay, is 1 and a 1, are there 2 1s in there? It's even. I am in fact getting the correct number. Whereas, if my friend got an erroneous number, somehow between here and there, this 1 got tacked on. 1, 2, 3, that's not an even number. So he will say, send it again. So parity, all it is, it's a means of error checking. And again, it's not the number. I know this is 4, and 4 is even. It's the number of bits, okay, that are 1, that's even or odd. Okay, let's again use another example of even parity. So I'm going to try to send the number 3. Even though 3 is an odd number, it has an even number of bits that are 1. Okay? So what do I have to add to that to make it even? I have to add a 0 because it's already even. I send it to my buddy. He gets 0, 0, 1, 1 with a parity bit of 0 if we're using even parity. And it's even. Check. Good to go. But let's say I've induced an error. Let's say I've dropped that 1 and put a 0 there. 1. There's only 1 in there. So that's odd. So that's bad. Okay, so I don't know what this number is supposed to represent, but it's obviously not what you intended to send to me, so send it again. Okay, so that's even parity. There's also something called odd parity. Odd parity is exactly opposite. Make the number and its parity bit odd. So let's use our same examples where I'm trying to send 4 and I'm adding a parity bit to make the number of ones odd. It's already odd. There's only 1. My parity bit is 0. Here's 3. How many ones do I have to add to make this one odd? Well, I should probably add 1 because that's 1, 2, 3, and now it's odd. Okay, let's use the number 5. And we're using an even parity system. What is the parity bit that I should append to this using even parity? There's 1, there's 2. It's already even, 0. Okay, so parity, all it is a means of error checking. And what we discussed here was using our all possible combinations of binary numbers in 4 bits in the particular case. We use several different languages: binary, 2's complement, BCD, which is basically a truncated version of traditional binary where the last 10, 11 on to 15 are invalid. And then we also talked about hex, which is using A, B, C, D, and F as a means of binary shorthand. We also discussed the gray code and parity.